Swayam Prabha. Digital India. Educated India.
Good morning to all of you. It's a pleasure to come and discuss some organic chemistry with you all. I am an organic chemist. My background is organic chemistry. Since the inception of RSIC, I have been part of the program every year and give at least 1 or 2 lectures to the students, which is very stimulating to me also. Let me start my lecture by asking one question. And you don't have to answer it immediately. You can take your time and think about it and answer it. What is a chemical bond? Is the question. Force of attraction between?
Or two atoms.
2 atoms.
Yes, sir. Force of attraction between any two molecules.
Okay, fine. We'll just take it for the time being. It's right. Okay. So I have at least 4 different answers here, right? We'll see what is the correct answer towards the end of the lecture. Okay. I want to talk to you about 2 concepts. One is called aromaticity. I don't know whether you heard about this concept or not. Okay. The other one is chirality.
Yes, sir.
You have heard about these 2 concepts. Stereoisomers, that is correct. Aromaticity is a concept in which you describe certain molecule with extraordinary thermodynamic stability because of delocalization of electrons. And benzene is one example of a molecule. This molecule has been in existence since 1800s when Faraday first distilled this from coal tar. This is a planar molecule with the 6 pi electrons present in the system. And the 6 pi electrons are supposed to be delocalized completely on the 6 carbon atoms. How do we know that this is the delocalized structure? How do we know experimentally?
Sir,
The average this is between a single bond and a double bond, right? How else do we know that this is a delocalized structure?
sir, generally when we have a saturated compound, if you add bromine water, the bromine will attack the double bond and it will the color of bromine, which is red color, will disappear because it attacks the unsaturated compound. But when we do this experiment with benzene, we don't see it because since the bond is delocalized across the entire molecule, bromine cannot attack the molecule, the double bond. So therefore the red color retains itself instead of being dissipated.
Suppose if it is not delocalized, will you be able to tell the difference between these two compounds? If it is not delocalized, you would say that this is connecting a single bond, the two bromines are attached, whereas here it is a double bond. So these are isomers. But we don't know whether it is isomers or not. Structurally, for example, you cannot distinguish these two compounds. There are no such thing as 1,2-dibromoethane, 1,2-dibromobenzene, two different forms of 1,2-dibromobenzene. There is only one 1,2-dibromobenzene. So Kekulé suggested alternating single bond and double bond for benzene structure, which was partly correct, except that he didn't say it is delocalized structure. Resonance structures. All right. Then came Huckel. He defined aromaticity as molecules having a planar structure, completely delocalized structure, having 4n plus 2 electrons, right? Planar, conjugated, cyclic. Kekulé's definition was probably the precise definition of aromaticity that we have. These 4n plus 2 electron systems have a peculiar property of being thermodynamically more stable than, let us say, for example, a 4n system. This is purely based on Huckel molecular orbital theory. One can say that these molecules have electronic energy levels like this. This is for benzene. 6 pi electron, you start filling up the electrons. You end up with this electronic configuration of this kind. The same thing if it is a 4n electron system. Four n electrons means it is a 4 electron system. Let us say n is equal to 1. If you follow the Hund's rule of maximum multiplicity, then these orbitals have to be singly occupied, right? Then only you get the maximum multiplicity of the electron spin. So apparently this electronic configuration is less stable compared to this electronic configuration. Both are arising from Huckel molecular orbital theory only. The extraordinary thermodynamic stability, how do we find out? You define the molecule as extraordinarily thermodynamically stable, but how do you find out that it is extraordinarily stable? The amount of energy? I am drawing this like this to indicate that it is not a delocalized structure. Now, if I do a hydrogenation experiment, all of them will give cyclohexane, right? This is a hypothetical molecule. The heat of hydrogenation is what we measure here, right? The heat of hydrogenation for cyclohexane is 28.6. This is around 56 point something, 57 points. This hypothetical molecule should have then 85.8 kilocalories per mole. If the Swayam trend continues, this is for one double bond hydrogenation, it is this much. It's an exothermic reaction, so it is minus 25.8, 28.6 kilocalories per mole. This is 57.2 kilocalories per mole. This is 85.8 kilocalories per mole. Benzene is surprisingly 49.8 kilocalories per mole. That means it is stable to an extent of 36 kilocalories per mole, which is the thermodynamic stability we are talking about. What should have been the difference between the 85.8 and 49.8 is 36 kilocalories per mole. To that extent, it is more stable than hexatriene. That's what it means. So, this is one criteria. One criterion for the thermodynamic stability is one criterion for the definition of an aromaticity. Aromatic molecules are thermodynamically more stable than the corresponding aliphatic equivalent molecule like the hexatriene and so on. Other than this, there is an important criterion that defines aromaticity is based on NMR spectroscopy. Nuclear magnetic resonance spectroscopy is probably the definitive answer to the aromaticity question. Can I remove this? Sorry? nuclear magnetic resonance spectroscopy. If you take proton, that is the nucleus of the hydrogen atom, right? Proton has what is known as nuclear spin. Just like electron spin, certain nucleus have spin as a property. This nuclear spin can be half integer, plus half, or minus half integer. So, if charged species is spinning, it will have its own magnetic momentum. So, it has two defined properties. One is magnetic moment, another one is angular momentum. Angular momentum is P and this is I. The ratio of these two is known as gamma, called gyromagnetic ratio. The nuclear spin is usually randomly oriented in the absence of any magnetic field.
Excuse me, sir. What exactly is the significance of the gyromagnetic ratio?
Gyromagnetic ratio is essentially the ratio between the nuclear magnetic moment to the nuclear angular momentum. It defines the property which is the magnetic property of the nucleus. Gyromagnetic ratio has a finite number. It is non-zero. If it is 0, then the nucleus is a magnetically inactive nucleus. If it is non-zero, then it is magnetically active nucleus. Only those nuclei which have the non-zero gyromagnetic ratio are useful for NMR spectroscopy. Proton is one such nucleus. All right. If the nuclear magnetic moment vector is randomly oriented in the absence of an external magnetic field, in the presence of an external magnetic field, we apply a magnetic field at this point, and the magnetic field strength increases in this direction. In that case, we have a splitting of the energy level like this, and the splitting of the energy level is now having minus half plus half, which are the spin states of the nuclear magnet. Certain number of nucleus will be aligning with the external magnetic field, certain number will be opposing the external magnetic field. These are the two energy levels that you have in the system. Now, if that is the case, if you apply an electromagnetic radiation, it should be possible to excite the nuclear spins in the lower level to the higher level. This is the essence of spectroscopy, right? You set up two energy levels and electromagnetic radiation of appropriate wavelength is applied, which promotes the electron probably in the electron spectroscopy. In this case, the nuclear spin to jump from lower level to higher level.
Sir, could you explain? We are applying a magnetic field downwards. So how is it coming to the Increasing?
This is in the right direction, it is increasing. This is the starting point I have marked as down.
Oh, okay. So it's okay.
Don't take these arrows literally.
So some of the electrons go downward and the others go upward.
It is
The
not the
nuclei,
electron we are dealing with
The
here.
nuclei.
Proton doesn't have any electron associated with this.
So what is actually going down? So like some are going up, you said some are coming down.
This is a nuclear spin state of the proton.
Proton.
Yeah. Nuclear spin state has two components, plus half component and minus half component. Whenever you have a magnetic field, you bring in an external magnet, it is going to align with the external magnetic field at certain points and oppose the external magnetic field at certain points. These are the two spin states of the proton that we have. And this is the energy gap associated with the nuclear spin states, and we can promote from the lower level spin state to the higher level spin state by applying appropriate electromagnetic radiation. The so-called appropriate electromagnetic radiation falls in the region of radio frequency. So, if you take a bunch of proton, let us say water, you take water, there is enough proton in water, right? Put it in a test tube and put it in between pole pieces of a magnet. You will have the absorption of the electromagnetic radiation only when the magnetic field is on. When the magnetic field is off, there is not going to be any absorption of electromagnetic field. Why? Because you have not set up the energy levels like this in the absence of external magnetic field. All of them are equal energy, so there is no absorption of electromagnetic radiation. So, this is essentially the crux of NMR spectroscopy. NMR spectroscopy is nothing but the absorption of electromagnetic radiation in the radio frequency region to a sample that is exposed to an external magnetic field. Whether you are doing an MRI imaging or just a spectroscopy, doesn't matter. This is the basic principle of NMR, nuclear magnetic resonance spectroscopy. The lower energy level will always have a finite excess of energy, finite excess of the species that we are measuring according to the Boltzmann's distribution law. This finite excess of nucleus is what we are promoting when you have the electromagnetic radiation applied here. That means at some point you can saturate the levels and the two levels can become equally populated. That is called the saturation. After which there is no absorption of light because of the saturation point of the . At saturation, there is no nucleus at the lower level.
No, you told when they're equally populated, it's called saturated level.
Yeah.
So there are some number of nuclei which are at the lower energy.
Yeah.
But it is at the equal number.
Yeah.
If we provide more energy than we were providing before,
You cannot promote any more of a
Why
nucleus.
is it, sir? Why after equal population at the higher and lower levels can we not excite the nuclei more?
It reaches a thermodynamically stable state when you have equal population between the two states.
But even when it is at thermodynamic equilibrium, if we provide energy to thermodynamic equilibrium,
What happens when you say saturation is that it is not a static phenomena. Saturation means this will go here, this will come back down here.
It is in dynamic.
Yeah, it is a dynamic equilibrium.
Sir,
Yeah.
sir, just like how we can change the direction of the equilibrium by changing some specific factors like concentration and temperature especially, which is energy. In this case, at this particular energy, like you're supplying this amount of energy, it's at this equilibrium. If we increase the energy, won't the equilibrium shift to a new state because the total energy of the system itself has increased after you supplied it?
If you heat the sample or cool the sample, that will affect the equilibrium. Okay? When you cool the sample, you will have more spins in the ground state compared to the upper state. And when you heat it, it will be in the equilibrium basically. I see. The equilibrium constant the equilibrium population can be perturbed by two things. One is temperature, the other one is magnetic field strength. Larger the magnetic field strength, higher is going to be the population at the lower level. Let me say here, as the gap increases between the alpha state and the beta state, or minus half state and the plus half state, the population here will keep on increasing because now you have a higher energy to jump. So the population at the lower level is going to be higher, much higher. Then you have a higher
Why is it that heat can shift the equilibrium but not EM radiation? Both are just forms of energy, right? So what's the difference?
the absorption of photon is different from the heat, essentially. Just think about it for a minute. This HU is proportional to B0 and gamma. Higher the gyromagnetic ratio, higher will be the gap of the alpha and beta states. So this will be equal to what it means is the photon frequency is directly proportional to the B0 and the gamma, which is the gyromagnetic ratio. These two parameters are, this is a constant for a given magnetic field that you are using in the laboratory. And this is a constant, God-given constant, which we cannot do anything about, because the gyromagnetic ratio is essentially defined by magnetic moment ratio, magnetic moment to angular momentum. Both these are constants, so one cannot do anything about it. So this means these two are constant for any proton that is present in the system will have finite energy requirement for the NMR phenomenon to take place. That means there are three types of protons in ethyl alcohol. all the three types of protons should come at the same frequency if this were to be true, right? But the shielding is not the same in this case. So this will be this is a shielding constant, which essentially means that if you have certain electron density around the proton, that can cause the shielding of the proton from the external magnetic field. Now, once you bring in the electron density into the picture, the electron density of these three hydrogens are different. So, essentially it will give three different peaks. So, that is how NMR spectroscopy is useful. If that did not happen, NMR spectroscopy would have been a useless technique actually. The fact that depending on the electron density around the nucleus will have different absorption of frequency, different frequency is essential for the electromagnetic radiation to be absorbed at different frequencies for the NMR spectroscopy.
Sir,
Yeah. If this were to be true, the B0 is something we choose in the laboratory, it is a constant. Gyromagnetic ratio is a God-given property of the nucleus. It's defined as the angular momentum to the magnetic momentum to the angular momentum. If these two are same, all the protons in the world will have the same frequency, because this is constant, this is constant, this is constant. So, this will be a constant irrespective of whatever proton you take, it will have the same frequency, which means you cannot tell a difference between the proton of the OH, proton of CH2, proton of CH3. The fact that there is a shielding factor, which is a sigma, comes into picture. This is a electron density around the nucleus. Once you bring a electron density around the nucleus, the electron density here is different from the electron density here and the electron density here. So, now for three different hydrogens, you will have three different frequencies, because around the hydrogen, each of the hydrogen, the electron density is different. Okay?
Sir, here we have two constants which we have to either calculate or experimentally verify. So, gamma and sigma, are they generally calculated or are they experimentally measured, and how would we measure them if they are measured?
That is the NMR spectroscopy all about. We'll deal with that now. So, let us come to aromaticity again. Now, let us say for example, I am applying a magnetic field in this direction. This is the plane of the benzene ring, and this is the direction perpendicular to that you are applying a magnetic field. Hypothetically, let us say this is the experiment we are doing. In the presence of an external magnetic field, these electrons will start rotating in this direction. This is the external magnetic field applied. This is the direction of the electron spin in the molecule. So it will generate its own magnetic field, right? Induced magnetic field. That induced magnetic field is going to be like this. The lines of forces of the induced magnetic field is going to be like this, such that it aligns with the external magnetic field here and opposes the external magnetic field here. This will be a donut shaped, these lines of forces around the circle of electrons is going to be like a donut shaped lines of forces is what is going to have. If this is the case, this is going to be de-shielded and this is going to be shielded with respect to the external magnetic field. The lines of forces tells you that this is aligning with the external magnetic field, this is opposing the external magnetic field. That means the proton that is present here is going to feel the shielding of the induced magnetic field by the external magnetic field, and the proton here, hypothetically let us say a proton is centered around there, that will have a lower external magnetic field being felt by this compared to higher external magnetic field being felt by the there is no such thing as proton inside benzene to start with. A hypothetical proton which is placed here will feel the external magnetic field to a lesser extent because of the opposing induced magnetic field. Here the induced magnetic field is aligning with the external magnetic field, so they will feel more. In other words, the frequency here higher than the frequency here. We have set up two regions where in the outer region of the benzene ring there is a higher frequency of radiation absorbed, and the core of the benzene ring lower frequency of the radio frequency is absorbed. This is called ring current effect. This is called ring current effect. Ring current, because of the pi electrons have the ring current, and the effect of the ring current is what is being felt by the induced magnetic field in this case.
Why the one in the outer ring feels more, the higher extent is where of the
Let us say this is passing through the center of the benzene ring, these lines of forces. Okay. Here it is opposing the external magnetic field, this is aligning with the external magnetic field because the induced magnetic field is in this direction. Okay. There is a rotation of the circulation of the electron in this direction in the presence of an external magnetic field. That causes or induces the magnetic field. The induced magnetic field is like this. The induced magnetic field is aligning with the external magnetic field, so it will be B0 plus certain value here. Here it will be B0 minus certain value here. That means it will come at a higher frequency. this will come at a lower frequency. If there is a proton here, it will come at a lower frequency. The peripheral protons of the benzene ring is going to be at a higher level of. Let us say, for example, we design a molecule like this in such a way that this CH2 is lying just above the plane of the benzene ring. This is called a paracyclophane. This is like, for example, a skipping rope is going around the benzene ring. That is a kind of motion that it will have at room temperature, right? Or you can imagine this is rotating on its axis like this particular manner. Here, this is a peripheral proton of the benzene ring. These are peripheral protons of the benzene ring. And this is an internal proton. In all practical purposes, this is going to be facing the center of the aromatic ring. So, based on the discussion we had, which hydrogens will come at a higher frequency and which hydrogens will come at a lower frequency? So, we have a scale called the delta scale, which is chemical shift scale. This is y axis and x axis. This is intensity of absorption. This is in parts per million. This is a dimensionless quantity. This is defined as, delta is defined as frequency of the sample minus frequency of the reference divided by spectrometer frequency. Frequency of the sample is easy to understand. Frequency of the sample will depend upon the magnetic field strength. So, you want to make it magnetic field strength independent, you just divide by the magnetic field strength actually, which is the spectrometer frequency. This is a reference, means it is a sample which is put in the actual sample, where you set this as a 0. This will have certain frequency value, artificially you set it as 0, and that makes it the quantity, a decent quantity to deal with. This is 0, this is 10 ppm. 0 to 10 ppm is the range of chemical shift value you can have for the proton NMR spectrum. And the region between 7 to 8 ppm is the aromatic peripheral hydrogen. This is experimentally measurable. Benzene is 7.3, for example, 7.3 ppm.
Sir, why are we taking the x-axis in reverse order, like 10, then 9, then 8, then 7 up to 0?
This is just a convention. There is no specific reason why we are taking it this.
So it's not like minus 10, or it's just 10.
It is 10. There is minus 10 here.
Okay, sir.
Okay. No, you can go from minus 250 to plus 250, doesn't matter. Typically, for organic molecules, the frequency will be confined to 0 to 10 ppm. If you make the molecule unusual, you can go up to minus 45. I will give you some examples of that kind. The point I am trying to build up here is that those hydrogens which are pointing towards the center of the benzene ring will have a lower frequency compared to these hydrogens which are peripheral hydrogens which will have a higher frequency. For example, this hydrogen A will come around 7.3 ppm. This will come at minus 1.5 ppm. Why is it minus 1.5? Because it is highly shielded. Chemical shift is a dimensionless quantity when it is expressed in parts per million. If you were measuring chemical shift in frequency terms, this will be dependent on the external magnetic field. So, the chemical shift I report will be different from the chemical shift you will report from a different spectrometer. In order to make it spectrometer independent, you divide it by the spectrometer frequency, then it becomes a dimensionless quantity. This is also magnetic field and this is also magnetic field, so it becomes nullified. The reference is essentially put so that you have a decent number to handle. For example, this can be 3159.8 or something, this can be 3259 point something, 6 or something. So, the difference of this will be somewhere around, let us say for example 100 ppm or so, right. You have two parameters you can vary. One is the magnetic field strength can be varied. Accordingly, the frequency of the irradiation has to vary, right. So, these are the two parameters you can vary. You can keep this as fixed number and vary this and scan the spectrum, or keep this as a fixed number and vary this as a scanned. When you say 400 megahertz NMR spectrometer, what we are referring is to the radio frequency 400 megahertz and the corresponding magnetic field strength is somewhere around 7.5 Tesla or something like that. So, these are the two experimentally variable quantities that we have in the NMR spectrometer. Normally, one is kept constant, the other one is scanned. Either of them can be kept constant and this other one can be scanned. So, here you see that it has gone all the way to minus 1.5 or so. What will be the value here? This is one carbon away from the these two hydrogens. They are not directly attached to the benzene ring, one carbon away they are attached to the benzene ring. Around 3 ppm it will come. This is purely because of the diamagnetic anisotropic effect. Anisotropic effect is what I described by the lines of forces of the, it is anisotropy because it is different regions, it has different effects. The core of the benzene it has an effect and the periphery of the benzene it has a different effect. These are monocyclic molecules with certain number of pi electrons. It's a cyclic conjugated systems, let us say, for example. They are called anilines. Anilines are cyclic compounds with alternating double bond and single bond. This is butadiene, highly reactive compound. Electronic configuration is like this. Hexatriene or benzene. According to Huckel molecular orbital theory, these are the electronic energy levels of the benzene ring. Cyclooctatetraene, for example, does not have a planar structure. It has a tub-shaped structure like this. In the planar structure, it will be highly delocalized, right? Those aniline which have 4n plus 2 electrons are called aromatic. 4n electron systems are called anti-aromatic. Anti-aromatic molecules are highly unstable molecules. They are just exactly opposite of the aromatic character. This will avoid the anti-aromaticity by becoming non-planar. That is the explanation generally given for this molecule to be a non-planar structure. The case of 10-annuline, these two hydrogens essentially occupy the same space when this is completely planar. This is like to be planar because it is aromatic, 10 electron system, 4n plus 2 system. But these two hydrogens are in the way of becoming planar for this molecule. So, this is a non-planar molecule. The steric hindrance of the two hydrogens interacting with each other is much higher than the stability it can get by being planar and aromatic and so on. So, the scientists overcome this problem by designing this molecule. By tying up these two hydrogens in the form of a methylene carbon.
Sir, won't that compound readily undergo dehydrogenation and form naphthalene? Won't it be very reactive like that?
No.
If you do not do this,
no, this will it will go to another conformation where it avoids the hydrogens, two hydrogens. It can rotate this bond still, right? The single bonds can be rotated. So, it can rotate itself out of the plane and out of the reach of these two hydrogens. All right. This is a very special molecule because it proves the aromaticity concept, the diamagnetic ring current effect concept, by directly putting these two hydrogens above the 10 electron system. 10-annuline These hydrogens come at minus 0.51 ppm, and these hydrogens here, they come around 7.27 to 6.98 ppm. So this clearly illustrates the point that the hydrogens are highly shielded when they are placed above the plane of the benzene ring or plane of the aromatic ring, and the peripheral hydrogens are highly de-shielded. Even more dramatic, just a second. Sorry, what is the question? This one, cyclooctatetraene. Cycloocta is 8-membered cyclic compound. Tetraenes means there are 4 double bonds. It is 8 aniline. This is 4 aniline. This is 6 aniline. This is 8 aniline. This is 10 aniline. Here, this is a dimethyl derivative. I cannot write the methyl within the bonding distance here and here. That's why I just elongated the methyl purposely to represent the methyl this direction. This is a 14 aniline system, right? Yes or no? This is a 14 aniline compound. So it is aromatic. Four n plus 2, n is equal to 3. This comes around minus 4.25. So you can see how de-shielded that particular compound is. Whereas these hydrogens come around 8.15 to 8.8 ppm. This molecule is like this. This is the plane of the aromatic ring system. One methyl is up here, one methyl is down here. Do you have some confusion? Yeah, it has 16 carbons, so what? The aniline is this point onwards. This compound can be reduced to the corresponding dianion. Using potassium metal, one can reduce it to the dianion. The dianion becomes aromatic or anti-aromatic now. This is anti-aromatic now. Because there are 14 electrons, when you add 2 more electrons, it becomes 16 electron species. 16 electron species is a anti-aromatic 4N system. What is interesting is the methyl groups now come around minus 4.35 ppm. Sorry, plus 24 ppm. The ring hydrogens minus 4.0 ppm. So NMR is definitely a valuable criteria for the decision to be made whether a compound is aromatic or not. You measure the NMR spectrum and look for the peaks. Corresponding region will be 7 to 9 ppm region, or if it is an anti-aromatic, it will be in the negative region. So such a decisive technique is NMR technique for the aromaticity concept. I'm sorry? Negative delta means there is a lot of electron density around the proton, which is being shielded by the electron density of the external magnetic field that you are applying. It is like, for example, you have one end of the NMR spectrum you have a bare proton, the other end of the NMR spectrum you have hydride ion. This has an electron cloud around it, so it will shield the external magnetic field. This doesn't have any electron present here, so it will not shield anything. It will become as a, at the most, solvation can shield this. Okay. So if this is coming around minus 6.5 ppm or something like this will come at plus 13.5 ppm. I'm just trying to give you an idea. Don't worry about the absolute numbers. This will be in the negative region, that will be in the positive region. Let us come to the question of what is a chemical bond. Any more answers? Overlap of atomic orbitals. That means you know everything about atomic orbitals, right? She is partly right. Can you go to the next one? This is a interesting article about the existence of the chemical bond, or questioning the existence of a chemical bond. This is a definitive statement by one of the famous Nobel laureates, Coulson. He is a theoretician doesn't believe in electrons and protons and orbitals and so on. One is almost tempted to say, at last I can almost see a bond, but that will never be, for a bond does not really exist at all. It is the most convenient fiction which we all have seen. It's convenient both to experimentalists as well as theoretical chemists. What makes him say this? He doesn't believe in electron densities, orbitals, shapes of orbitals and so on. They are all theoretical imagination, that's what he says. Quantum mechanics tells you there is a p orbital which is lobe is dumbbell shaped, but nobody has seen the dumbbell shaped electron density. Go to the next one. This is a longer version of the same story he is talking about. Chemical bond first related to deposition of 2 electrons. Remember, one has never seen an electron. So he points out the problems that we have in defining things. Chemical bond can never be defined in one sentence actually. This is a picture we normally see, right? If a chemical bond is somewhere in the equilibrium distance, it comes together and the energy is lower, and that is the distance that you measure is the bond length distance, and the energy of the bond is corresponding to the bond energy here. If you push it further down, because of the compression of the nucleus with each other, it goes up in energy. That is essentially repulsion, whereas here there is no attraction of energy, so it is 2 different units of the atoms, let us say. But then go back. If this is a definition, every chemical bond should have a finite bond length, right? Carbon-hydrogen bond length should be same more or less everywhere that you see carbon-hydrogen bond length. Carbon-carbon bond length, for example, you will see almost same amount. With a slight variation is acceptable, but the variations are really dramatic in certain cases. Go to the next one. Here, bond dissociation energy is plotted against the bond length angstroms. So, the bond dissociation energy becomes 0 when the bond length is 1.75. Otherwise, if you go from here to here, the bond dissociation energy and the bond lengths are correlatable by a linear correlation. That means you can vary from 1.3 to 1.7 ppm, which is a large variation to define a bond length, right? Experimentally observed facts. Next. Ethane, for example, has a bond length of 1.54 angstroms or 154 picometers. That is a normal saturated carbon-carbon bond length that one would expect to have. But remember, depends on the molecule, depending on the steric congestion, the bond can stretch itself and it can go to higher values, length values. For example, here hexaaryl ethane. Aryl groups are these highly sterically hindered groups. These are essentially put there only to make steric hindrance. Right? So it becomes 1.67 angstroms or 167 picometer. Here this is adamantane structure. Adamantane is a molecule This is adamantane molecule. This is a diadamantane kind of a structure is what we have. Again, because of steric hindrance, it is 1.74, 1.70 angstroms is what the bond length is. Now you begin to doubt whether carbon-carbon bond length is 1.55 or go to the next one. This is even higher. The iodines are causing the size of the iodine is very big. So that is causing the steric hindrance 1.73 angstroms, for example. And the last one is 1.8 angstrom. Next one. This is the longest reported carbon-carbon bond length, 1.93. How can you have a bond length of 1.93 still call it a bond? That is a question that is put to audience now. The molecule is quite stable. I mean, you can isolate it and characterize it. The bond lengths are determined by X-ray diffraction method. So there is nothing wrong in the values. These are not theoretically calculated values. They are experimental values. So for that thing.
Sir, won't the bond length be just whichever length at which the system has the lowest energy? So depending on the external conditions also, if you see in that graph, the bond length is generally where the graph is at its lowest, where like the lowest energy is there. But then that energy value will depend upon like the external, it will depend a bit upon the external steric hindrance and all that. So that's why the bond length changes based on the conditions also. So you can define
All
bond
I am
length
saying
as
is this picture is wrong. I can have the picture here, or I can have the picture here, cut off here. These are all different bond lengths, right? To make it absolutely like this, to define very precisely, is the problem. Do you understand? I have no problem if you define it here, for example, or define it here. But to define it within certain precision here is going to be problematic because different molecules are going to have different bond lengths. What you are saying is different molecules will have different profile as well. That is also true. But then how do you define bond lengths?
Sir, we can define bond length as the length at which the system has the least energy. The molecule has the least energy.
Least
energy.
potential energy.
So that will take into consideration the entire profile of the energy curve.
It's debatable actually. Anyway, keep thinking about it and see whether you can come up with a better definition of bond length and chemical bond. Okay. Let us move on to chirality now. அதிலே கண்டினியூ பண்ணலாமே. இது இருக்கட்டும். What is chiral? Yeah.
Sir, the hydrogens that are on the outer, closer to the outer ring of the benzene, sir, which feel the higher extent of the magnetic field, do they have a higher value of ppm?
Yes.
Okay.
That is correct. The peripheral hydrogens are having the higher delta value. Yeah.
The core ones have a lower.
Lower delta value. What is chirality? Handedness. Handedness of what?
Of the molecule. The way in which
Does it have to be molecule?
asymmetrical carbon kind of.
I want a very general definition of chirality, which can be applied to any system. Carbon is specific, I don't want that.
Sir, non-superimposable isomers
That corresponds to only molecules.
or non-superimposable like
I can have a coffee cup which is chiral.
A non-symmetrical field will have a chiral.
superimposable with its mirror image.
Is this chiral? Why do you say it is chiral?
But that's not where the mirror is not that way. So if there's some text on it, it depends on the plane. If there's some text on the cup, then no.
No, nothing. This is a
So
plain.
you can rotate it like this. You can rotate it like this, so it will be fine.
So what is chirality?
Any figure which does not have a plane or center of symmetry or axis of symmetry is named as chirality. You can't rotate the mirror images, but you can't rotate them. Or
You can't rotate or
So,
do anything to get the mirror image. You
so
just have
could
to
we
use
say it's
flipping.
chiral in that plane? Because there's no rotation like outward. It's in a 3D space it's possible to rotate like that, but in a planar space, in that 2D plane, you can't rotate like that. So. So, but like in the plane, that sort of rotation would not exist, right?
Sorry?
In a plane, in that plane.
Why I can have a cup and rotate it like that? Nothing prevents me from rotating it like that. Why not? A coffee mug can be rotated to brought in and superimposed on top of this. An object is said to be chiral if its mirror image cannot be superimposed on top of itself. Let us say, for example, I have a smiley cup. Is that chiral or achiral?
if you have smiley on both the cups, it will be some both the same elements on both the cups. Then it will be. No, it will be on the other side. Even if you rotate it, it will go on the other side. No, I meant if it's on the front. Yeah, but then when you rotate it 180 degrees, it goes sorry, yeah, so then it's not chiral. It's not chiral. It is chiral. No, it is chiral.
This is chiral because I rotated 180 degree and this is hiding behind in the cup. The smiley is on the other side of the cup now. Again, it is non-superimposable. So, handedness is chirality. Can you name something that is chiral? Name an object that is chiral. Chirality is handedness, so hand has to be chiral, right? Anything else is chiral? How about a pair of shoes? A pair of gloves? Pair of gloves and pair of shoes, they are not chiral? What about the jada you have got? Earlobes are chiral, yes. When it comes to molecules, molecular chirality has something to do with this non-superimposability of molecules. This is a molecule, this is a mirror image of the molecule, correct? And they are non-superimposable on top of each other. If we try to lift it and bring it here, this bromine will superimpose with the chlorine will superimpose with the bromine. All the three groups will not be superimposable on top of each other. This is because they are arranged in a certain fashion. If you are looking at the molecule through the carbon hydrogen bond, this is what you will see. This is the tetrahedral carbon. Tetrahedral carbon, lift it up like this and look through the carbon hydrogen bond. You will see chlorine here above bromine, and above fluorine and bromine will be there. So these are different ways of looking at the same molecule. This molecule, for example, viewed along the CH axis, is very clear that this is a right-handed fluorine bromine chlorine. This is a left-handed fluorine bromine chlorine. Exactly mirror image of each other. That is a chiral molecule, right? Chiral objects are plenty. You don't have to define chiral object only with the molecules. Any object, if it doesn't have a plane of symmetry, it can be chiral. Next. Organic molecules having chiral centers are exhibiting a stereochemistry, a particular stereochemistry called stereoisomers called optical isomers. Yeah. These are compounds which are natural products. This is limonene, R-limonene and S-limonene. They differ in the chirality of this carbon here. They are mirror images of each other, non-superimposable. So they are chiral in nature. The important thing is that they have different properties. Even though there is a slight change in the stereochemistry of the carbon here to there, the rest of the structure remains the same. Our olfactory sensors are very specific. They can smell the oranges from apples, oranges from lemons, right? This is because of the chiral nature of the olfactory sensors, which can discriminate between these two molecules in terms of the chirality of the molecule. Next.
What does the R and S signify?
R and S signifies the absolute configuration of the center, which is a chiral center. Okay. You had this molecule seen this. There is a CH in the backside of the. Here, atomic number wise, this is atomic number wise high 1, atomic number wise high 2, number 3, right? So the least of the atomic number is the hydrogen, which is 4 in the place. That is kept away from the viewer. The viewer look at it from the point of view of clockwise or anti-clockwise rotation. If it is a clockwise rotation, it is called R. If it is an anti-clockwise rotation, this is S isomer. For simple organic molecules, this is the easiest way to decide on the absolute configuration of the molecule. Here is another example, carbone, spearmint odor or caraway seeds, depends on whether you have R carbone or S carbone. The R and S corresponds to the absolute configuration at this center here. Next. This is an artificial sweetener called NutraSweet. It is an amide, it is a peptide, and it has 2 chiral centers. Only these 2 chiral centers are correct chiral centers are corresponding to the sweetness of the drink. If we change the configuration here, it will not be sweet at all. So the stereochemistry is very important for the particular property there we are looking at. Next. It is important to have the optical isomers properly characterized for the reason that they will have different properties. The properties are that only one enantiomer is active, the other one is inactive. For example, when you take ibuprofen, Brufen as a tablet, this is ibuprofen, this is a chiral center. So it can exist in two isomeric forms, R form and S form. If the R form alone is active and S form is not active, there is no point in taking 1:1 mixture of these two compounds inside our body. 50% of it will be useless and 50% will be active in the nature. So only one isomer is active, the other isomer is inactive. That is okay, at least they have equal and similar activity. Both enantiomers are active but different potencies. The last one is the most dangerous one. One isomer is active, the other one is toxic. That will make it really bad to take a optically active medicine. Right? So, next.
Sir, in the first point it's mentioned that only one enantiomer is active, and in the third point it says both are active.
Both are active to different potencies.
Okay.
One can take a microgram quantity to cure the disease, other one will take gram quantities to take the potencies are different. This is an experiment that was done during the 1960s. Thalidomide is a molecule which has a chiral center here, and one of the isomer, namely R isomer, is sleep inducing, S isomer is teratogenic. Teratogenic means it will deform the formation of the fetus to different extent. So these are children born because of the side effect of the morning sickness curing agent thalidomide. This has been banned since then, and now there is a new focus on this molecule, that whether it can be used as an anti-cancer agent because it is a teratogenic in nature. So it may be useful if you change the molecule to some suitable derivative, it may be useful to.
So don't we have any separation techniques for RNAs?
Yeah, there are separation techniques, chromatographic techniques can be used. Next. These are all chirality associated with insect pheromones. Pheromones are chemical substances used for communication among insects, and you have to have a right kind of stereochemistry to recognize a particular species. If you change the chirality here, it may not recognize its own species, for example. So chirality is extremely important in these cases. That's what I am trying to illustrate. Next. Atorvastatin is a medicine people take for high blood pressure or cholesterol problems and so on. That has two chiral centers, and it has to be the right chiral center molecule to act as a medicine. So one has to be careful taking these medicines in the racemic form. Racemic is a mixture of 1:1 mixture of the enantiomers. Enantiomers are the optical isomers of the chiral molecule. 1:1 mixture of the enantiomers is called racemic mixture. This is a chiral center. This is a chiral center. Here, this is a chiral center. Four different groups should be attached to a carbon, right? Next. Chiral molecules are either left-handed or right-handed. They rotate the plane of the plane polarized light. What is a plane polarized light? What is a plane polarized light? the magnetic vector and the electronic vector are confined to one particular plane. That is called a plane polarized light. Yeah, that is correct. The plane polarized light rotates the plane of the plane polarized light. The phenomenon is called optical rotation. One enantiomer rotates the plane to the right hand side direction, the other one enantiomer will rotate it in the opposite direction to an equal amount. 1:1 mixture is called the racemic mixture and not optically active. Next. Molecule with more than one chiral center, if you have n chiral center, then the number of isomers become more and more complex, 2 to the power n number of isomers you can have. So if you have 10 chiral centers in a molecule, you had it. How many isomers you will have? 2 to the power 10. Yeah, we are not defining any symmetry at this point. If they are same configuration or same atoms are connected, then it will reduce. Yeah. Yeah. These are completely different groups are attached to the point that we are trying to make. Next. Constitutionally disymmetric and constitutionally symmetric molecule is what you are talking about. Here is a case where all the 3 groups are different on both the carbons. So this can have 4 different groups are there. Next one. Here you see ABC group is there in the bottom carbon and ABC group is there in the top bottom also. So it is constitutionally symmetrical. So there one of the isomer will be a meso isomer. That will reduce the number of this isomer here is a meso isomer. Meso isomer has a plane of symmetry because of the same groups that are being attached to ABC, ABC and so on. So as a result of that, you have a one reduced isomer. This has only 3 isomers. Next. These are all some molecules which are constitutionally symmetrical in nature, asymmetrical in nature and symmetrical in nature. Tartaric acid has 3 isomers, D isomer, L isomer and meso isomer, right? Similarly, erythrose and threose are sugar units, 4 carbon sugars, and they are constitutionally unsymmetrical, so they will have all the 4 isomers present in the system. Erythrose? No, erythrose is not constitutionally symmetrical. Top one is aldehyde, bottom one is CH2OH. Next. Next. Only mirror symmetry or rotation reflection symmetry should be absent in the molecule. It can have rotational symmetry, axis of symmetry is permissible. Here is a molecule where you can rotate the molecule along the CH bond. Let us say CH bond is like a stick, I am rotating this. This will come here, this will come here and this will come here, right? This is a chiral molecule, that is what I am trying to say. Here for example, mirror image relationship is there. 3-fold axis of rotation is there in this molecule. This is not superimposable on top of each other, because if you take this and put it like this, the hydrogen will come in the front. That is why you should have a good imagination of 3-dimensional structures in your mind to not to make a mistake of this. Next. Other than center of chirality, we have been dealing only with center of chirality so far. You can have plane of chirality, axis of chirality. Molecule possessing chiral planes are called chiral in nature. Finally, helical chirality, chirality due to a twist. These are diastereoisomers. These are cis-trans isomers, right? Cis-trans isomers are called diastereoisomers. Diastereoisomers are stereoisomers which are neither mirror image nor superimposable on top of each other. This can exist only in the cis form and the trans form, and the cis form and trans form are not superimposable on top of each other. This is not due to chirality. You can superimpose this on top of each other, the mirror images, but not diastereoisomers are entirely different configuration of the molecule. Next, these are allenes. Allenes are having an axis of symmetry. When you have a C double bond C double bond C, these are on the plane of the blackboard. So these will be above the plane of the blackboard. This will be below the plane of the blackboard. In other words, it is this plane is like this plane is like this. The central carbon is a sp carbon. So it will have the orbitals in the particular direction. This, okay. So if you are viewing the molecule from this side along the carbon axis, this is what you will see. You will see the chlorine, the hydrogen and the chlorine, and the hydrogen and the chlorine like this. These are the groups attached to the front carbon, here this carbon, the backside carbon, these are the two groups attached to the backside carbon. This is a non-planar chiral molecule. There is an axis of chirality. The chirality is because of the axis, which is this axis, which is the C2 symmetric axis of the molecule. In spite of having a C2 symmetry, it is still chiral because it doesn't have a plane of chirality. Next. These are some molecules called atropisomers.
Sir, I have a doubt, sir. In this molecule, sir, why is only one side not in the plane of the blackboard? Like, why can't both either be in the plane of the blackboard or not in the plane of the blackboard?
This is the reason. This will bond only horizontally, this will bond only vertically, right? These are some molecules which are called atropisomers. This is because of inability to turn around here. The rotation is missing here. You cannot rotate the carbon-carbon bond completely here because of the steric hindrance of the X and Y. Here, this is a spirocyclic molecule. One cannot rotate the molecule without breaking a bond. And you can see here vancomycin is a very complex natural product. Vancomycin is one of the anti-cancer drugs that are used. And naturally occurring vancomycin is a chiral optically isomer, pure isomer, which is this configuration. You can see the number of stereoisomers is unimaginable here because of the complexity of the molecule that we have here. Next. This is a planar chiral molecule. This is called the 2,2-paracyclophane. Is this chiral? This is chiral. Why are you so reluctant to shake your head like this? It's not chiral. You have a plane of symmetry this way, plane of symmetry this way. So it is a chiral molecule. Suppose I put a substituent anywhere in this molecule. Doesn't matter whether I put it here or put it here. Doesn't matter. Any one of the places I can put. The molecule becomes chiral. Right? So this is a molecule with a plane of chirality. This plane is chiral plane because of the fact that when you look at it from the top, you will have a handedness here and the corresponding you will have an anti-clockwise direction. That is why it is planar chiral in nature. Ferrocene itself is achiral, but if you introduce two groups in ferrocene, then it becomes chiral. These are some organometallic compounds which are chiral in nature. Next.
Sir?
These are helically chiral.
Sir, in that the BR is not, it's not in the, like, it's not in the plane, right? It's out or...
BR is projecting towards you. Benzene, naphthalene, anthracene, tetracene, pentacene, hexacene, they are all linearly fused aromatic system. One can have angularly fused aromatic system. By the time you come to the hexacene, you see it is start touching the other portion of the, if it is coming on the same plane, it will interact with these hydrogens. So it will not be possible to have a planar structure. It goes above or below the plane and twists itself to go to a helical structure. That is how the helical structures are formed here. This is a 6-helicene. 6-helicene has this particular structure. Next. That's all. Chirality is a very fundamental concept in stereochemistry, organic chemistry, and without understanding the chirality of the molecules, it's rather difficult to study stereochemistry of the systems. So I hope in these two lectures I have been able to give you some idea of the chirality and aromaticity of the molecules.